Hello, and welcome to this presentation on radian measure. We're going to introduce the formula S is equal to r theta to solve some geometrical problems. S in this case is the arc length, shown here. R is the radius of the sector, and theta is the angle subtended. A brief introduction here. We use angles to measure the amount by which a line has turned through. And there are two main angle units in use. The first one, the one you're very familiar with, will be the degree, usually in decimal form, such as 36.5. Although there is what's termed as sexagesimal notation, which is the degrees, minutes and seconds notation. We'll briefly recap that in a moment. Essentially, the degree is based on an arbitrary number of 360. In other words, in one revolution, there are 360 degrees. However, with high-level mathematics study and high-level study in both science and engineering, often the radian is used as an angular measure. Unlike the degree, it's not based on an arbitrary number, for example 360. The definition of a radian is based upon the property of a circle. The radian is sometimes termed the natural measure or the true mathematical measure of an angle. Radians help to simplify formulae and calculations. The radian measure formula that we'll be using is S is equal to R multiplied by theta. Here's the definition of a radian. 1 radian is the angle theta subtended at the centre of a circle by an arc S equal in length to the radius R of the circle. In other words, from the diagram above, when the arc length S of the sector of our circle is the same length as radius R, then the angle theta subtended or enclosed within the sector of the circle is 1 radian. I would suggest to you from here on in within your engineering studies that unless we are told otherwise, the angle is assumed to be in radians. So unless you see the degree symbol stated within calculations, assume the angles are in radians. This slide is just for backdrop and it relates to the angular units of measure. Decimal notation, don't forget, is always in terms of degree, and we're probably very familiar with decimal notation. There is also what's called sexagesimal notation. This is called the degrees, minutes and seconds notation. So this is used in some of the questions. Don't forget, in terms of degrees, there are 360 degrees in a circle. In terms of minutes, if we're in sexagesimal notation, there are 60 minutes in a degree. And we know, that by 60 with a little dash. And as far as seconds are concerned, there are 60 seconds in a minute, so 60 double dash. Okay, so we can do conversions between decimal degrees and sexagesimal notation, shown below in example 1, so how to do this manually, but we would always do this on a calculator where we need to. Okay, just for reference then, if we wanted to convert angles from decimal degrees into degrees, minutes and seconds, there's a button on our calculator. It looks like this. On most calculators for degrees, minutes and seconds, some calculators actually have DMS written on the button instead of the symbols there, but it means the same thing. So for example, go straight to an illustration here. If I wanted to calculate 37.6 degrees in terms of degrees, minutes and seconds, all I do is type 37.6 on my calculator, I press equals, and then I press the DMS button, and I get the value of 37 degrees and 36 minutes. So I've gone from decimal degrees into sexagesimal notation. If I want to reverse the process, I want to go from 37 degrees 36 minutes into decimal degrees. This is the way I do it on the calculator. I type in 37, and then I press my DMS button so the calculator knows that's 37 degrees. I then type in 36 and press the DMS button. The calculator knows that's minutes. If I had seconds, I would then type the seconds in and press the button again. In this case, I don't. So I press equals, that puts it into the calculator's memory, and if you press then DMS button one more time, you get the 37.6 degrees. So what you're seeing there is the extent of the knowledge you need to understand how to do the conversions in the solution we're going to look at, where they occur. Let's now consider radians and radian measure. Given our formula, S is equal to R multiplied by theta, if we make the arc lengths of our sector equal to the radius, then the angle subtended, theta, would equal to 1 radian. That's a definition of a radian. If we now make the arc lengths of our sector of a circle, S, is equal to twice the radius, so in other words this length here, our arc length of our sector is now 2r, and on the left hand side of the equation the S becomes 2r, on the right hand side that equals to the r theta from our formula, and we can clearly see that the r on the left hand side cancels with the r on the right hand side, so the angle subtended in this case is theta of 2 radians. So this angle here would be 2 radians. If we now make the arc lengths S equal to 3 times the radius, so this length of arc here, shown in the sketch, is now equal to 3 times the radius, then on the left hand side S is 3r, on the right hand side that equals to r times theta, and if we again cancel the r on the left with the r on the right, we can see that the angle subtended in this case would be theta of 3 radians. So we have 3 radians in here. Now if we consider the circumference of a circle, which can be written as S is equal to pi d, where S is the circumference of the circle and d is the diameter, or we could write the circumference of a circle S in terms of radius, so it becomes 2 multiplied by the pi multiplied by the r. So now letting S is equal to 2 pi r on the left hand side of our equation, and that equals to r theta on the right hand side. If we were to cancel the r's off this time, either side of our equation, we find that the angle theta now is 2 pi radians. So in other words, if we consider the circle circumference, or in other words 1 revolution from here right the way around to here, so thus the length of the arc in this case, 2 pi r, which is the circumference of a circle. So we can now say that in 1 revolution we have 2 pi radians. So we're very familiar when using degrees that 1 revolution is equivalent to 360 degrees, but now we can say that 1 revolution is also equivalent to 2 pi radian. And that's a very important value to remember. Alternatively, we can show that 1 radian is equal to 360 degrees divided by 2 pi radians, and that evaluates to approximately 57.295 degrees. So 1 radian is 57.3 degrees to 1 decimal place. Nominally, as a very crude estimate, we can say that 1 radian is 60 degrees, to give us a feel for the conversions of degrees to radians. This slide illustrates the initial problems that students have in finding arc length S using the formula S equal to r theta. In problem 1, the angle in the question is specified in what is termed pi radians. So the angle theta is equal to 5 pi upon 6. However, in problem 2, the angle specified in the question is in decimal degrees. So the angle here, theta, is 75.6 degrees. Now what's essential here is that before we use the S is equal to r theta formula, we must convert the angle theta into radians. That's absolutely essential. Whenever we use this formula here, we always have to have our angle theta in radians. It will not work if our angle is in degrees. It's very important to remember. Here's a couple of examples where a standard formula required the use of radians. In this particular question, we were trying to find the volume of acid in a tank, knowing the sludge depth in the tank that was given to us, and also knowing the air dimension left in the tank. So the formula we use here to calculate the area, and so the volume of sludge, and then the area, and so the volume of air, was given here. The formula for volume was a half r squared, and in brackets it's phi minus sine of phi, and then multiplied by the length of the vessel. What we need to be very careful of here is that the angle phi is actually in radians. In the calculations I undertook, you can see here I've worked out the angles in degrees, 33.18 degrees and 23.5 degrees. but I've calculated them in terms of radians here to use them in the formula. That's a formula that's derived in radians, and so we need to use radians when undertaking the calculations. If you use degrees there, you would get the wrong answer. Here's another illustration of where radians are required in use of a formula. It says in the question, for the shape that we're currently considering here, the angle alpha shown here must be greater than pi upon 2. And when we see the pi upon 2, that means we're using radians by default. As I mentioned at the beginning of the presentation, we should always assume radians now unless told otherwise. But when we see the pi's in the angles, then that's a clear indication we're using radians. So in other words, where the alpha symbol is shown in the equation here, we have to use radians. And one final example of where we need to use radians, this formula here for working out deflection at the mid-length of a strut, shown here, is given as negative E multiplied by the sec of ml upon 2. Now sec is a function that's actually the reciprocal of the cosine function, so sec of theta is actually 1 upon cos theta. So because that's a trig function, we now need to be careful which angle measure we're using, degrees or radians. And in this higher level study, more complicated formula, the radian is the angle that we should always use. So in this particular question, when I was undertaking my calculations, I had to make sure that my calculator was in radians mode because the angle we were using in the formula for the 1 upon the cosine was actually radians. I'll talk more about different modes on the calculator later on in the presentation. In other words, what the past few slides have been showing us is that at high level study in engineering science, we often need to use the radian because the formula we're using at high level is derived in terms of radian, not degree. So in summary here, the radian is used within high level mathematics study and is the preferred unit of angular measure. The radian simplifies both derivations and calculations. The definition of a radian is based on the property of a circle. And a radian is the angle theta subtended at the centre of a circle, position O on our diagram here, of an arc length S, whose length equals the circle's radius R. So for radian measure, the angle in radian theta is equal to the arc length S divided by the radius of the circle R. And that's the essential formula we'll be using for most of the presentation. Let's now consider briefly the relationship between degrees and radians. On the circle shown here, we start on this position of 0 and we rotate anti-clockwise every 30 degrees, shown here 30, 60, 90, 120, etc., right the way around till we come back to 360 degrees in the one revolution. If we now consider that in terms of pi radians, then 0 to 360 degrees, one revolution, would be 0 to 2 pi radians. So if one complete revolution relates to an angle of 2 pi in radians, then half a revolution equates to an angle pi, or 180 degrees. That means a quarter of the revolution is 90 degrees, or pi upon 2, and 3/4 of a revolution is 270 degrees, or 3 pi upon 2, 1.5 pi. If we now divide the 180 degrees into 6, we get 30 degrees, so dividing pi by 6, we get 30 degree equivalent in radians. So 30 degrees is pi upon 6. 60 degrees would be 2 pi upon 6, which cancels to pi upon 3. 120 degrees would be 4 pi upon 6, which cancels to 2 pi upon 3. 150 degrees is 5 pi upon 6, and 180 degrees, as we said previously, is pi radians. 210 degrees would be 7 pi upon 6 radians, etc. The angle of 45 degrees would be a line through here, and 45 degrees would be in radians pi upon 4. If we want to undertake conversions between degrees and radians and vice versa, then the conversions are shown below. For degrees to radians, we multiply our angle in degrees by pi upon 180, or 2 pi upon 360, whichever you prefer. So in other words, having an angle given to us as 45 degrees, and we want to convert that into pi radians and radians, then 45 degrees multiplied by pi upon 180 is equal to pi upon 4. The 45 degrees and the 180 cancel to 1 and 4. And then we can work that in terms of decimal if we want to, 0.7854 radians. And then converting an angle in radians to degrees, we use the conversion of the angle in radians multiplied by 180 degrees divided by pi. So example, if we're asked to convert 1.25 radians to degrees, so the conversion is 1.25 multiplied by 180 degrees divided by pi radians, and that's 71.62 degrees. Question 1. Using a calculator, we're asked to convert the following angles into radians and pi radians. So question 1, we're given the angle of 75 degrees, so to convert that into radians, we multiply by pi and divide by 180. That produces a value of 1.309 radians, or in terms of pi radians, that would be 5 pi divided by 12. So mod calculators will give the answer in pi radians automatically. Question 2, we're asked to convert 135 degrees into radians and pi radians. So multiplying by pi divided by 180, we find we get 2.356 radians, or 3 pi upon 4 radians, or decimal 0.75 pi radians. Question 3, we're asked to convert 27 degrees and 12 minutes into radians. There's a hint here to convert to decimal form first of all, as shown on the previous slides, and then into radian form. So solutions are 0.4747 radians, or 34 pi upon 225. Again, the pi radians format might be given in the calculator you're using. I'll let you review the last two questions at your own pace, but don't forget to convert first of all the sexagesimal notation into decimal notation. Question 2, we're now asked to convert the following angles into degrees and pi radians. In question 1, we've got 3.14159 radians, so multiply by 180 degrees and divide by pi, we will get a value of approximately 180 degrees, or pi radians. Question 2, we're given 0.5 radians. Again, the conversion is multiplied by 180 divided by pi, so the answers are 28.65 degrees, or 0.1592 pi radians. I'll let you review the other three questions at your own pace. Example 3D. Using radian measure, we're asked to find the arc length in the following questions. Given that r is the radius, theta is the angle subtended by the arc, we've got to find the length of the arc, symbol s. So in question 1, we're given that r is equal to 12 centimeters and the angle theta is 5 pi divided by 6, so that's obviously in radians. So in part 1, calculating the arc length, symbol s, we've got our r, we've got our theta, and it's already in radians, so we simply use the formula as written, s is equal to r theta, that becomes 12 multiplied by 5 pi divided by 6, which gives an answer, if you want to leave it in terms of pi, would be 10 pi, that's 10 multiplied by pi centimeters, or the actual answer, working it out, we find that the arc length is 31.416 centimeters. Part 2, we're now given that the radius r is 36 millimeters and the angle is given as 75 degrees and 36 minutes. So now to calculate the arc length s, we need to be careful. The radius is fine, it's given in terms of 36 millimeters, but the angle theta is given in terms of sexagesimal notation. So we first of all need to convert that into decimal notation. We're using the previous conversion on our calculators. Type in 75, press the DMS button. Type in 36, press the DMS button and press equals. That will give us the value of decimal degrees, 75.6 degrees. The actual conversion is shown here, but you don't need to actually do that. Just use your calculator DMS button. So once we've got the angle in terms of 75.6 degrees, we can then convert that into radians. So the angle theta is going to be 75.6 degrees multiplied by pi divided by 180. That gives an angle in radians of 1.319 radians. Now we can calculate the arc length using the S is equal to r theta formula. It will be an r of 36 multiplied by an angle of 1.319 radians. So the arc length S in the above diagram is 47.5 millimeters. So be careful with the information given. In the first part of the example above, we were given the angle theta in terms of radians, so we could use the S equals to r theta formula immediately. But in the second part of the example, we were given the angle in terms of degrees, so we have to convert that first of all to radians before we use the S equal to r theta formula. Question 3, we're asked to use radian measure to find again the arc length S in the following questions. In question 1, we're given the radius of 3 meters and the angle subtended of 2 pi divided by 3. And in part 2, we're given the radius of 22 millimeters and the angle subtended is in terms of degrees and minutes. Answers are shown in the brackets below each of the questions. I would encourage you to stop the presentation for a moment and attempt question 3 parts 1 and 2. The full work solutions are shown on the following slide. Question 3, solution shown. Again, we're asked to use radian measure to calculate the arc length S. In part 1, we're given the radius of 3 meters and the angle theta as 2 pi upon 3 radians. So in this case, we can use the formula S equals to r theta directly to work out the arc length S. But in part 2, we need to be more careful. We're given the radius is 22 millimeters, but the angle theta here is in sets of decimal notation, degrees and minutes. So the first thing we need to do is to convert the degrees in minutes into decimal degrees and then into radians. Then we can apply the S equals to r theta formula and calculate the value of S. Question 4. We're asked to use radian measure again to find the unknown quantities in the questions below. In part 1, we're given the arc length S this time is 63 millimeters and we're given the angle subtended 11 pi divided by 6 radians. We're asked to find the radius r. So that will involve some transposition. You'll need to rearrange the equation for r and then put the values of S and theta into the equation to find the answer given here. In part 2, this time we're given S of 1.5 meters and the radius of 0.75 meters. We're asked to find the angle theta in this case. Again, that would involve some transposition. You need to rearrange the equation to find angle theta as a subject and then put the values of S and R into the equation. Note that the final answer given is in terms of degrees, so be careful when you're evaluating the final solution. I would encourage you to stop the presentation and attempt question 4, but the full work solutions are shown on the following slides. Question 4, solution. In part 1, we're given the value of the arc length S, 63 millimeters, and we're given angle theta 11 pi upon 6 radians. We're asked to calculate the radius r. So, part 1, from S equal to r theta, we first of all need to rearrange the formula to make the r the subject. So dividing both sides by theta, then the radius r is equal to S divided by theta. As the angle theta in part 1 is already given in radians, we can use the formula directly to find the radius. So in this case, the radius is 10.938 millimeters. In part 2, we're given arc length S is equal to 1.5 meters, and the radius of our sector is 0.75 meters. We're asked to find the angle theta in this case. So in part 2, using S equal to r theta, we rearrange to find the angle theta, so divide both sides by r in this case. So theta is S divided by r. Inserting the values for S and r, theta is 1.5 divided by 0.75, so that's 2 radians. But notice in the answer given, they want the final answer in terms of degrees. So using our conversion, 2 radians multiplied by 180 degrees divided by pi, producing the final answer for theta of 114.6 degrees. I would suggest you stop the presentation and just think through those solutions carefully for yourself. Calculations that involve trigonometric functions. When evaluating expressions involving sine, cos, or tan functions, the correct calculator mode is essential. So where the angles are given in degrees, we use degree mode, and when they're given in radians, we use the radian mode. You'll find on your calculators at the top of the screen a small D, R or G. The D stands for degree mode, the R stands for radians, and the G stands for grades. Conventionally we only use degrees or radians. So the point we're trying to make here is that we need to be in the correct mode when undertaking calculations using trig functions. So reviewing the example calculations, example 1, we're given that x is equal to 32 multiplied by the sine of 45 degrees. Now we can clearly see that's a degree angle, so we need our calculator set in degree mode, and evaluating 32 multiplied by the sine of 45 degrees produces a value of 22.627. So our calculator was in degree mode then. In example 2, we're asked to calculate x, given that is equals to 32 multiplied by the sine of 2. Now in this case that is not degrees, that will be radians, there's no degree symbol there. And don't forget there's a big difference between 2 degrees and 2 radians, because 1 radian is nominally 60 degrees, so 2 radians is actually around 120 degrees, which is a much larger angle of course than the 2 degrees. So we need to be very careful about which mode we're in. If we use degree mode here, we will get the wrong answer. We need to be in radians mode. So 32 multiplied by the sine of 2, when you're in radians mode, will give you 29.1. So that was radians mode. Reviewing example 3, x is equal to 4.5 multiplied by the cos of 4.1888. Again, no degree symbol, so we'll assume we'll be in radians mode, and the answer in that case would be negative 2.25. And finally with example 4, x is equal to the tan of pi upon 3 minus cos of 1. Again, the pi in the angle really gives away it's in radians, but there's no degree symbols anyway, so we would assume radians in this case. So if we're in radian mode, then the answer would be 1.192. Just be careful, this slide is trying to emphasize that we need to be in the correct mode when undertaking calculations of all the trig functions, and depending on the calculator type you're using, I've shown a particular type here, you need to find out how to change the mode from degrees to radians, and of course back again. Question 5. We're asked to calculate the value of x in each of the following cases, and we've got to use the correct calculator mode. I would suggest you stop the presentation for a moment and undertake the calculations for parts 1 through to 4. Assuming you're in the correct mode, you should find the answers on the right hand side in the brackets are correct. I encourage you to stop the presentation for a moment and undertake the calculations. So in part 1 you should have been in radians mode because the angle is given in radians and a degree symbol there. In part 2 we've clearly got degree mode required there. In part 3 we should be in radians mode. We can clearly see we've got a pi in the angle and of course no degree symbol. And finally in part 4 again we should be in radian mode because the angles are in radians. The following questions are now practical examples of using radian measure. They're contextualised. So in question 6 you're given a sheet metal component shown in the sketch, and the angle subtended is 75 degrees shown here. With both the inner shown here and the outer shown here sectors of the component. So we're using the S equal to R theta formula again. I would encourage you to stop the presentation and attempt this question. Basically you're using the S equals to R theta formula twice, but we're using different radii. The answers are shown in the brackets and the full work solutions are shown on the following slide. Here's question 6 solution. The first thing we need to do of course is to convert the angle of 75 degrees into radians. So that was done here, angle theta. 75 degrees multiplied by pi divided by 180 degrees produce an angle of 1.309 radians. So you must convert the angle to radians before you use the formula S equals to r theta. And calculating the inner arc lengths, the S is equal to r theta, the inner radius is 35 millimeters shown here, and we multiply that by the angle theta in radians of 1.309, produces an arc length of 45.815 millimeters. So we've calculated the inner arc lengths shown here. And finally, calculating the outer arc lengths, S equals to r theta. The r now is 58 millimeters, that's shown here, and the angle is as per above. That gives us a value of 75.922 millimeters for the outer arc length, which is this arc length shown here. Question 7 is a slightly more complicated contextualized question. We're given a drive-in pulley, shown in the sketch. We're asked to calculate the angle of lap for the pulley, angle theta, shown here. Now for reference, in belt drive calculations, the angle of lap is a particularly important characteristic of the belt drive configuration. And basically what it relates to is the angle that associated with the contact of the belt with the pulley. So it would be the angle shown there in yellow. So in this particular question, we're given the length of the belt contact S with the pulley is 375 millimeters. And we're given the diameter D of the pulley is 300 millimeters. So we have to find the angle theta and state our final answer in terms of degrees. I would suggest you stop the presentation, think carefully through the question as posed and the information given, and attempt the solution. The full work solution is shown on the following slide. Question 7, solution shown here. So we're given a drive-in pulley, shown in the sketch below, and asked to calculate the angle of lap theta. First thing to notice in the question is that we were given the diameter of the pulley, D, which was 300 millimeters. But obviously in the calculations we're using, we need to know what the radius is. So the first thing I've shown here is the calculation for radius. So r is equal to the diameter divided by 2. So 300 divided by 2 is 150 millimeters. We've got our value of r now for the problem. So now from the question we are given the arc length S, which is 375 millimeters. So that's this value around here. It's S value 375 millimeters. That's the contact of the belt with the pulley. So now that we know the value of r and S, we can calculate the angle theta. So now we're going to calculate the angle of lap theta. So from S equals to r theta, dividing both sides by r, we find that theta is equal to S divided by r. Given S is 375 millimeters, and r is equal to 150 millimeters from above, that gives us an angle of 2.5 radians. Notice that the question wants the angle in terms of degrees though, so we have to finally calculate the angle in degrees. So finally converting the angle from radians to degrees, the angle will be 2.5 radians multiplied by 180 divided by pi. So 143.2 degrees, or to the nearest degree, angle theta is 143 degrees. The final part of this presentation relates to calculating areas of a sector of a circle. Now the following formula you've probably seen before. It calculates the area of a sector of a circle in terms of degrees. So in this case, capital A is equal to area of a sector, and that's equal to the area of a circle, pi r squared, multiplied by the proportion of the sector of the circle. In other words, the angle theta for the sector divided by, in this case, 360 degrees. We're using degrees here. For example 1a, the angle subtended by the sector of a circle is 135 degrees, and that's shown here. Theta is 135 degrees. The radius of the circle is 50 millimeters. R is equal to 50 millimeters. We've got to calculate the area of the sector. So using the above formula, the A is equal to the pi r squared multiplied by the angle theta of the sector divided by 360 degrees. So in this case that's pi multiplied by 50 squared, the radius is 50, and we multiply that by the 135 degrees divided by 360 degrees. 360 degrees in the circle as we know. Evaluating, the area of the sector is 2,945.2 millimeters squared. So that calculation was undertaken using degrees. So example 2a. The angle subtended by the sector of a circle is again 135 degrees, shown here. The radius of the circle is 50 millimeters, same as before, shown here. We've got to determine the area of the sector, but this time we're going to use the radian formula derived on the previous slide. So the first thing we need to do now is to calculate the angle in terms of radians. So we're given angle theta in the question is 135 degrees, multiplied by pi, divided by 180, we find the angle in terms of radians, 2.356 radians. Now we can use the formula derived previously of A is equal to r squared theta divided by 2, where of course the angle theta is now in radians. So from the information given, the r is 50, so 50 squared multiplied by the angle of 2.356 radians divided by 2 produces the same calculation as we shown on the previous slide when using degrees of 2,945.2 millimeters squared. So example 1a and example 2a are basically the same calculations, but 1a is undertaken using degrees and 2a is undertaken using radians. Question 8 relates to a sheet metal component shown in the sketch. The angle subtended is 75 degrees, shown here. We're asked to determine the area of the sector using the formula A is equal to r squared theta divided by 2. Don't forget the angle theta here has to be in radians. The answer is shown in the brackets at the bottom of the question. Notice that all the dimensions are in millimeters here. I would encourage you to start the presentation and calculate the area of that sector using the radians formula. The full work solution is shown on the following slide. Question 8 solution. Given a sheet metal component in the form of a sector of a circle has a subtended angle of 75 degrees, shown here, we're asked to calculate the area of the sector using the formula A is equal to r squared theta divided by 2, where theta will be in radians. So from the solution shown here, the first thing we do is calculate the angle in radians. So angle theta is 75 degrees multiplied by pi divided by 180, so the angle in radians is 1.309. Now we can use the above formula to calculate the area, so area is equal to r squared theta divided by 2, so r above is 58 millimeters, so 58 squared multiplied by the angle in radians divided by 2, produces an area of 2,201.7 millimeters squared. Here's question 9 related to a feed hopper using a foundry, so fairly complicated context here. I will let you consider this question at your own pace, read the question carefully, extract the information from the question, label it appropriately, and then solve as required in the question. The answers are given in the brackets here. The full work solutions are shown on the following slides. Question 9, solution. We're given the feed hopper within a foundry incorporates a hinge shuttered door, which is the shape of a sector of a circle, shown in the sketch below. The length around the arc is 0.7 meters, so that's the arc length shown here, 0.7 meters, and the angle subtended is 55 degrees, that's shown here. We're asked to determine the lengths of one of the straight sides, so that would be the radius, for example here, and also the area covered by the shutter. We're told to use the equation A is equal to r squared theta divided by 2 to find the area. So the first thing we do is to calculate the angle in radians. So angle theta was given as 55 degrees in the question. Multiplying by pi divided by 180, we find the angle is 0.96 radians. So part 1, we need to calculate the radius of the sector. So from S is equal to r theta, the first thing we do is rearrange to find r. So divide both sides by theta. R is equal to S divided by theta. The S is 0.7 meters. The angle theta is 0.96 radians. So that gives a value of 0.729 meters for the r. And in part 2, we're asked to calculate the area of the sector. So A is equal to r squared theta divided by 2. The r in this case is 0.729 from above, so 0.729 squared, multiplied by the angle theta divided by 2. That gives a value of 0.255 meters squared. Tutorial questions continued. Question 10. We're asked to convert the following angles making use of the conversions shown below. Radians to degrees conversion and degrees to radians conversion. So on the left hand side here, question A through to J requires us to calculate the angles from radians into degrees. Where possible, try and not use a calculator to form the calculations, but the answers shown in the brackets on the right hand side. And in the right hand column here, we're asked to convert the angles in degrees to pi radians and radians. So there will be two answers for questions K through to T. The first answer in the brackets is the pi radians, and the second answer is the decimal radians. Don't forget pi divided by 6 is equal to 0.5226, but the pi radians are the exact answer and the decimals are effectively approximations. I would encourage you to stop the presentation and attempt question 10. Tutorial questions continued. Question 11 through to 13, I'll let you review them at your own pace. Notice the answers are shown in the brackets on the right hand side. And finally, question 14, you're asked to find the lengths of the spring bracket shown using radian measure. You're given various pieces of information to help you with this solution. The answer for the total length of the spring bracket is 294.2 millimeters. Again, I would strongly encourage you to attempt these tutorial questions. For reference, here's the bibliography used to help develop the presentation. And I hope this has been of interest to you, and thank you for viewing.